So sorry I was out of town. I had to sort of leave town urgently. So I'm glad that Richard was able to take over. Hopefully it was okay. Yeah, so just announcement. So an extension on the problem set. I guess it's problem set 8, 7. Okay, problem set 8, 7 until Monday, Tuesday. Which would you prefer? Maybe let's say Tuesday, because I'm going to hand out the next one on Tuesday anyway. So that'll be Tuesday, and it'll be whatever the day Tuesday is. It's March something, some day in March. I'm not sure exactly what day in March it is. What day is it? The 17th? Okay, good. Okay, so today what I want to do is continue with our development of Yang-Mills theory. And in particular, we've spent the last 3 lectures or so understanding how to construct the sort of classical action of Yang-Mills theory and write down the equations of motion. And what I want to do today and next class is work out the Feynman rules for Yang-Mills theory. Okay? So in principle, now that we have an action for Yang-Mills theory, it should be reasonably straightforward to work out the Feynman rules. But there are really 2 obstacles that arise when you want to start writing out the Feynman rules and using them to calculate even at tree level in Yang-Mills theory. The first is that the just tree level calculations can be vastly more complicated for Yang-Mills theory than they can for other sorts of theories. So even simple, say, gluon to gluon scattering amplitudes can, if you're not careful, involve the sum of thousands of different diagrams once you include all of the various index structures and things like that that are present. So one needs to develop some sort of efficient techniques to organize your calculations. Okay, so we're going to have to spend a little bit of time on that. But today what I want to do is talk about something that is perhaps an even more important technical and conceptual leap that we're going to have to do in order to develop Feynman rules for Yang-Mills theory. So in particular, what we're going to need to do is carefully revisit something that we sort of glossed over a little bit when we studied U-Wunsch gauge theory, that is to say electromagnetism, and think about it a little bit more deeply. So today what I'm going to do is introduce the notion of a ghost and what's called the Fadeev-Popov gauge fixing procedure, which is going to be an extremely clever way in order to understand exactly how the gauge fixing procedure works in Yang-Mills theory. It's a bit formal, so there's some kind of technical tricks that I'm going to be introducing today that I think are shocking and appalling the first time that you see them. So I just want to give you a bit of a word of warning, but it is something that if you think about it a little bit, does end up making a lot of sense, and it's extremely clever, okay, which is always good. So, but before I get into all of that stuff, let me just remind you of where we are and where we're going. So the basic degrees of freedom of Yang-Mills theory are the gauge field, which is a vector field A mu, that actually is represented by some n by n matrix. So we can think of this as a collection of vector fields labeled by an index A, where we expand the gauge field in this basis of generators TA, and A is an index that runs from 1 up to D, where D is the dimension of the gauge group. So it would be 3 in the case of SU2 and 8 in the case of SU3. And the basic principle of Yang-Mills theory is that the theory should be invariant under a gauge transformation. So when we initially introduced Yang-Mills theory, our gauge transformation was associated with an element of the gauge group. But an infinitesimal gauge transformation, as you have learned on your problem set, and we learned not on Tuesday, but during our earlier lecture on Yang-Mills theory, can be represented by an element of the Lie algebra that we'll call theta with an index A, that is a function of your position in space-time. And under a gauge transformation, that is generated by this under a gauge transformation associated with these gauge parameters theta A, the gauge field A transforms much like it does in electromagnetism, namely a mu goes to a mu plus the derivative of the gauge parameter theta. But there's a correction term that essentially involves the fact that our gauge group is now non-trivial, so that the structure constants F, A, B, C are non-trivial. And it's really this extra term in the gauge transformation that's going to lead to all of the subtleties with gauge fixing in Yang-Mills theory that we'll have to talk about today. And one thing that I think is worth emphasizing even at this early stage is that unlike the case of electromagnetism, that is to say U1 gauge theory, the gauge field A transforms even if theta is a constant. So that means that this gauge parameter theta is really playing a somewhat different role in Yang-Mills theory than it did in electromagnetism, where those structure constants F just vanished. Now, it turns out that we can write this gauge variation of our Yang-Mills field A slightly more economically if we remember that the covariant derivative d mu, the covariant derivative d mu, defined in some representation that we could label R, is the differential operator where we correct the usual derivative d by dx mu by a term that is linear in the gauge field A, and whose expansion in terms of this gauge field is given by some matrices T that are representations of the Lie algebra. So they obey the fundamental commutation relation of our Lie group G. So here R is, so this is not, okay, it looks a little like I'm writing trace. I'm not writing trace here. It's T sub R. So the T sub R are the representation matrices in a representation R of the gauge group G. So, for example, in the fundamental representation, these TAs are n by n matrices. On your problem set, you're going to be working them out explicitly in the Gelman basis for SU3, for SU2. The fundamental basis in the two-dimensional representation is given by the Pauli matrices. But as you're familiar with in the case of SU2, there are all sorts of other representations that we could consider. One interesting representation is known as the adjoint representation. That is a d-dimensional representation where the representation matrices TA are now d by d matrices whose entries are just given by the structure constants of the group. Okay. So this is something that you hopefully met last time. Now, so here, A is labeling which representation matrix we're talking about, and B and C are the matrix indices that run from 1 up to D. So this is a d-dimensional representation. And it's a reasonably straightforward exercise to show that the matrices whose entries are given by the structure constants, as I've written them here, do indeed obey the Lie algebra. That just follows from the Jacobi identity for the Lie algebra. And that's hopefully something that you encountered last time. And if you didn't work through it explicitly in class last time, it's easy enough to check. Did Richard do it last time? Did he prove to you guys that these satisfy the appropriate algebra? It's a straightforward exercise using the Jacobi identity. Okay, he didn't. Okay, so now I know what's going to be on your next problem set. Okay. So this is a representation always looking for good problems. So that's an exercise. Okay. So why is the adjoint representation useful? Well, just compare this form for the representation matrices in the adjoint to this particular combination of the derivative of theta and the structure constant FABC times A times theta. And you'll see that you can economically write the expression for the variation of the gauge field under a gauge transformation in term as the covariant derivative in the adjoint representation. Okay. So let's just write that out a little bit more explicitly. So what was this? This is d mu theta A plus FABC A mu B theta C. And so let me just write this out a little bit more explicitly. So here, when I wrote down the covariant derivative, I didn't write out explicitly the index that ran over the representation. Okay? Whereas here, I've written out the index explicitly. They're the B and C indices. So let's just rewrite this a little bit, writing out all of our indices explicitly. So this is, you could write this as delta AC d by dx mu minus I A mu times FABC, which is just up to a factor of I. So that was an A mu B. The representation matrix T in the adjoint representation. So here I could put a little adjoint subscript just to remind ourselves that it's in the adjoint representation. And so this then is just the covariant derivative in the adjoint representation. And here I've included an index AC, just writing out the index in the adjoint representation explicitly. So if you wanted to write this a little bit more implicitly, you might write this as d mu in the adjoint of theta superscript A. Okay. So that's nice. I mean, we shouldn't be surprised at this point that covariant derivatives are appearing all over the place. So for example, just as a reminder, another place that covariant derivatives appear is that if you compute the commutator of two covariant derivatives in a given representation, then you just get what we call the curvature F, or the field strength F, of the gauge field. So here, you've seen this formula before, but there's no reason not to be reminded of it. The curvature of the Yang-Mills field is given by an expression that's very similar to the curvature or to the field strength in electromagnetism, except that it contains this additional term, quadratic in the gauge field, that involves the structure constants FABC. And just as a comment, remember that these structure constants are antisymmetric in their indices ABC. And so because of that, you could antisymmetrize those two gauge fields, A mu B and A mu C, to conclude that just as in electromagnetism, the field strength F mu nu is antisymmetric in the mu and nu indices. Okay. So although it's not immediately obvious, the fact that the field strength is antisymmetric means that F mu nu is antisymmetric in its two indices, just like in electromagnetism. Now, there are a few interesting differences from electromagnetism, which I'm just going to point out here. So the first is that, unlike in electromagnetism, F mu nu is not gauge invariant, but rather it transforms under a gauge transformation in a way that is often summarized as the statement that F mu nu is gauge covariant. Okay. So we saw this explicitly when we worked out how F transforms under a finite gauge transformation, transformed by conjugation with that matrix that we called V. And when you work it out infinitesimally, that just means that there's no derivatives involved. And you get an expression that looks like that. Okay. So don't worry if some of these are unclear. You're going to check them all on your problem set if you haven't already. Good. And so because of that, if you want to construct an action which is gauge invariant rather than gauge covariant, you need to do something like take the trace. So, for example, the action F mu nu A, F mu nu A is gauge invariant. And of course, it's also Lorentz invariant because we've contracted those mu and nu indices together. So, I mean, this is a relatively simple symbol for something with a lot of terms. So mu and nu are so mu and nu both run from 1 up to 4. A runs from 1 up to the dimension of the gauge group. So, for example, in QCD, where the dimension of the gauge group is 8, let's see, this would be 6 times 8. It would be a sum of 48 different terms. Okay. So, because an antisymmetric 2-index tensor has 6 degrees of freedom. One comment that I'll make that I think is worth noting, just as an additional point of divergence from electromagnetism, is that unlike the case of E&M, even if A is equal to a constant, F can be non-zero. In particular, if A is a constant, but the different values, the different A mu's regarded as n by n matrices don't commute with one another, then this commutator appearing here could be non-zero. And that's unlike the case of electromagnetism, where, for example, if you had a constant value of the electrostatic potential, the electric field strength would be equal to 0. So in principle now, it's completely straightforward to derive the Feynman rules from the action. And that's an exercise that we're going to go through next class. So the total action will be given by the Yang-Mills action plus a matter action plus other sorts of interaction terms, where, for example, the matter action, if we have Dirac fermion, for example, transforming in a particular representation of the gauge group, would just be the usual Dirac action with the replacement of D by a gauge covariant derivative. I should mention that actually the Yang-Mills Lagrangian that I've written up here is actually not the most general possible kinetic term that we could write for a Yang-Mills field. There actually, it turns out, is an additional possible kinetic term which is sometimes referred to as the theta term. So it's given by some coupling constant, so there's just some conventional factor of 32 pi squared. And because F is an antisymmetric 2-index tensor, it's possible to construct a different Lorentz invariant from the field strength F where you take two f's and you contract them. You don't, instead of contracting the mu nu indices of the two f's together, you contract them both with the 4-index epsilon tensor. So for those of you who aren't familiar with it, the epsilon tensor is the 4-index object whose entries are given by 1 or -1, depending on whether mu nu rho sigma are an even or an odd permutation of 0, 1, 2, and 3. So if you've seen general relativity, for example, or even the formulation of electromagnetism in index notation, then you've probably seen this epsilon tensor. And if not, don't worry, I'll probably give you a problem related to it on the next problem set. So this possible addition to the action of Yang-Mills theory is interesting for a couple of possible different reasons. So one interesting fact about it is that unlike the kinetic term that we wrote down above, this is parity odd rather than parity even. So it picks up a minus sign under spatial reflections. Sorry, this plug just doesn't seem to be working. Okay, there we go. Another, I think, very interesting feature of this possible addition to the Yang-Mills Lagrangian is that, in fact, L theta does not affect either the equations of motion or the Feynman rules. In fact, it turns out that L theta is topological in a way that I think I'll have you prove on the next problem set. Did I give you, for Yang, in the case of electromagnetism, I gave you this problem? Okay. So, so you'll probably, maybe I won't make you play around with it even more than for the case of Yang-Mills theory. I'll see if I can come up with a fun problem. Okay. And because it doesn't affect the equations of motion or the Feynman rules, it does not affect perturbative physics. However, it can affect non-perturbative physics. So it does enter in the computation of non-perturbative effects. But those are really, I think, beyond the scope of what we're going to consider in this class. And so for the purposes of this class, we'll largely be forgetting about this term. However, I should just comment that this theta parameter, this new coupling constant, can be measured by thinking about its contributions to non-perturbative effects in QCD. And it's observed to be very small in QCD. That is to say, unobservably small. So the possible values of theta have been bounded experimentally in QCD, and within experimental error, it appears to be 0. And various mechanisms have been proposed. So most famously, something known as the Peccei-Quinn mechanism to explain the smallness of the theta parameter. Naively, one might say, well, this term is parity odd. Maybe parity symmetry is a symmetry that we would like to impose on the Lagrangian of nature. But it turns out that the standard model actually breaks parity symmetry already in ways that have been observed. So a priori, we don't have a symmetry that would guarantee that this is set equal to 0. So instead, what people have proposed is that there's a new field known as the axion, which dynamically sets the value of theta equal to 0. Essentially, the coupling constant theta is promoted to a new field, and then the dynamics of this field then make the value of this parameter unobservably small. Interestingly enough, the axion is one of the leading candidates for the dark matter particle. So there's a lot of interesting physics that goes into this term. But I'm really mentioning it as an aside because aside from maybe some problem, if I can think of one, on the problem set, we're not going to be talking about this term further in this course. Okay. So it's then straightforward, for example, to write down the equations of motion and the Feynman rules coming from this action. So for example, the equation of motion. So the equation of motion for Yang-Mills theory, well, you have the equations of motion for the matter field, for example, which are the Euler-Lagrange equations that you get by varying the action with respect to psi and setting it equal to 0. So not surprisingly, those are just the usual equations of motion, namely the Dirac equation, with the Dirac operator corrected to account for the fact that you now have a covariant derivative with respect to the gauge field, as opposed to the usual partial derivative. And the equation of motion for the gauge field is also not so hard to work out. I think I assigned it to you on a problem set. Is that right? I think you're working out the equations of motion. You're working out the equations of motion? Okay. So again, you might not be surprised to learn that the equations of motion can be most succinctly written when you write them in terms of covariant derivatives. So you can almost just guess what the equations of motion are by analogy with electromagnetism. So remember that Maxwell's equations can be written as d mu f mu nu is equal to the current J nu. And the equations of motion of Yang-Mills theory that you obtain by varying the action with respect to the gauge field take almost exactly the same form, except now the partial derivative has been replaced by a covariant derivative, which reflects the fact that f transforms in the adjoint representation. So in particular, when I write the derivative, so here I won't bother contracting the indices, and write the derivative more generally. So when I write the covariant derivative of f mu nu with respect to x rho, we have the usual derivative term, so d rho f mu nu a, plus a correction term, just as we found when we wrote down the covariant derivative in the adjoint representation for the gauge parameter theta, that involves, well, sorry, that's a rho, that involves a times f. And the current here is given by almost exactly what you would expect. So this is the current associated with the gauge transformation G, the rotation of that vector's worth, or the rotation of the n component vector of Dirac spinors psi. So remember, in the case of electromagnetism, the current was just psi bar gamma mu psi. In Yang-Mills theory, this just gets generalized to take into account the fact that the psi's now transform in some representation of a more complicated gauge group. And so, as you'll see on your problem set, the current takes the form of gamma mu, psi bar gamma mu times the representation matrix TA times psi. Okay. So this is the Yang-Mills current. So I'm going through the equations of motion and the gauge transformations rather quickly because I could work it all out. It would probably take me all class to work everything out in terms of the indices. But it's a sufficiently detailed calculation that you're not going to learn anything unless you do it yourselves, so you will. So you'll work these all out in more detail on a problem set. So now, at least in principle, I could go ahead and write down the Feynman rules simply by expanding out the action order by order in my fields, A and psi. I could use the quadratic terms to work out the propagators, and then there are cubic and quartic terms describing the interactions of the various fields that would lead to cubic and quartic interaction vertices in the Feynman diagrams. And indeed, that's what I'm going to do next class. But before I do that, we really need to clarify one very important issue. In defining Yang-Mills theory, which is that gauge invariance must be treated rather carefully. Now actually, there's a sort of interesting history involved with the argument that I'm now going to give, which is that Yang and Mills originally proposed the Yang-Mills Lagrangian and Yang-Mills theory almost more than 50 years ago. But for a long time, it was not quite clear how, once one includes quantum mechanical effects, you can actually preserve gauge invariance. So there was a lot of worry that gauge invariance would be broken quantum mechanically. It wasn't really clear if these Yang-Mills theories made sense quantum mechanically. So for example, when we studied electromagnetism, I gave at least a sketchy proof, or if not a proof, an argument that if you work order by order in quantum electrodynamics, the Ward identities are still obeyed, which reflects the fact that gauge invariance is preserved at all orders in perturbation theory. And for quite some time, actually, it was not at all clear whether one could preserve gauge invariance in Yang-Mills theory in the same way. So it was not at all clear that Yang-Mills theories could be written down as consistent gauge invariant theories even at the quantum mechanical level. And so it was realized, actually only in the 70s, by Fadeev and Popov, that there's actually a rather clever trick that you can do which allows you to treat gauge invariance completely systematically. It's a bit more complicated than in electromagnetism. It requires the introduction of some new fields into the theory that essentially play the role of enforcing gauge invariance. And interestingly enough, the Fadeev-Popov procedure, which I'm going to describe now, is the first time, I think, in the history of physics that the path integral approach to quantum mechanics was actually useful. So the path integral approach to quantum mechanics was really developed in the 40s, maybe even the late 30s by Feynman. It was anticipated some decades before that by Dirac. But it was sort of a curiosity that really was not viewed as having any true fundamental importance. And it was only when Fadeev and Popov used the Feynman path integral to come up with the appropriate gauge fixing procedure for Yang-Mills theory that the path integral was recognized, I think, as a genuinely useful tool in the study of quantum mechanics and quantum field theory. Okay. So what I'm going to, the argument, so usually when we study physics, even in quantum mechanics, even so far in this class when I studied the development of quantum field theory, the path integral is introduced as a nice conceptual way of visualizing things, but not a particularly useful calculational tool. It doesn't give you anything that you couldn't already have derived using Hamiltonian techniques or canonical quantization or something like that. So for example, when we derived Feynman diagrams, first we derived them by studying the Schwinger-Dyson equations, and then we used the Feynman path integral. Curiously enough, the Fadeev-Popov procedure that we're going to be discussing now is really one idea that I think is vastly clear in the path integral formulation. I won't say that you couldn't study it without the path integral formulation, because I think that's probably not quite true, but it's certainly something that I don't think people would have really ever figured out if it weren't for the path integral formulation. Okay. I don't know if that's even true. It's sort of hard to argue about some counterfactual universe where people never understood path integrals, but it's interesting at least to think about. Okay. So let me explain the basic idea to you after that sort of long prologue. So what we're interested in doing is calculating some sort of path integral where we integrate over all of our fields, the gauge fields A. And for example, you might, if you want to calculate a scattering process with some number of external legs, introduce some sources, which are represented by some currents J mu A that are contracted with our gauge fields A mu A. And the point is that this path integral should be interpreted as an integral over all gauge fields modulo gauge transformations. In particular, if you integrate over the gauge parameter as well, that is to say you include in this path integral all gauge equivalent values of A mu, you'll essentially be overcounting because you'll be integrating over too many degrees of freedom. Okay. So if you integrate over gauge equivalent A mu, then you'll be overcounting. And so what we need to do is come up with a careful way of making sure that we only count one A mu in each equivalence class under gauge transformation. Now, this is not something that we worried about too much when we thought about electromagnetism. And it's worth thinking a little bit about why it is when we studied QED we didn't think about this terribly carefully. The reason is the following. So in electromagnetism, the behavior of the gauge field under a gauge transformation is rather simple. It just changes by a total derivative. Or if you want to work this out in momentum space, if I denote by A mu tilde, the gauge field in momentum space, the Fourier transformed gauge field, and by lambda tilde, the Fourier transformed gauge parameter, then you're just shifting A mu by K mu times lambda. Okay. And so that means that if we think about the path integral in momentum space, so you can think about the integration over all gauge fields A as an integral in momentum space. So you take the product over all possible momentum modes K, and then you integrate over the Fourier, value of the gauge field in a particular momentum sector K. And if you want to only integrate over one A mu per gauge equivalence class, then all you need to do is throw out the gauge degrees of freedom by integrating only over those A mu's which are perpendicular to K mu. So in particular, under a gauge transformation, A mu will shift by something proportional to K mu. Okay? So if you just integrate only over those A mu's perpendicular to K mu, then you've automatically chosen just one value of A for each gauge equivalence class. In other words, in the path integral, we just throw out those fluctuations of the gauge field that are perpendicular to the momentum vector K mu. Okay. Now you can immediately see what the problem is in Yang-Mills theory. So in Yang-Mills theory, as we noted before, the variation of the gauge field is actually a covariant derivative of the gauge parameter rather than a partial derivative of the gauge parameter. And so the gauge transformation is not of the Fourier transformed Yang-Mills field A is not proportional to Canyon. And so it's not just the longitudinal polarization of the photon that you need to discard if you only want to integrate over gauge inequivalent field configurations. So what we need to do is be a little bit more careful. And that's exactly what I'm going to do now. But before I proceed, let me see if there are any questions. Everything's clear so far?
One question. So this matrices T appears like in various forms, but they should not appear in the durable.
Well, I mean, I guess I'm not quite sure.
Well, let's say we have a transformation which depends on the representation.
Yes.
If you choose a different representation, then the transformation rules will change.
Yeah, so you could do, for example, a change of basis,
Yeah.
which would rotate the t's among one another. Is that what you mean?
No, but that shouldn't affect the observable. Which means that in the observable, we
Yeah,
should
so-
not guarantee.
Yeah, I guess I'm not quite sure what you mean. I mean,
If we calculate the
A
observable-
sort of, the index A labels essentially different polarizations, if you like. I mean, I guess you wouldn't call them physical polarizations, but different components of the gauge field. So, you know, it's really the case that in SU3 there are 8 different flavors, if you like. Well, I shouldn't call them flavor. Flavor has a different meaning in particle physics. But there are 8 different types of photon. And they all transform among one another in some complicated way. But
The observable shouldn't depend on our chart.
I mean, the observables are going to be gauge invariant. Maybe I'm not quite clear what your question is.
Well, I'm trying to see if all those T's should disappear in the observable.
Well, at the end of the day, one could, of course, consider scattering amplitudes of the different types of gluons with one another, gluons being the particle that you get when you quantize A. And you'll have to make a choice of basis. But maybe I'm not quite clear on what your question is. Why don't we, I mean, so we're gonna spend this class and all next class developing the Feynman rules. So maybe if when we talk about external states and Feynman diagrams and stuff like that, it's still unclear, maybe you can ask your question again. Okay. So remember, the idea is that we really want to include only one gauge configuration per equivalence class under gauge transformation. So what we're going to do is just introduce some function, which is going to be a functional of our gauge field A. And they're going to be D of these, so I've labeled them by an index A that runs from 1 up to D, the dimension of the gauge group. And I want it to have the property such that if you set G equals to 0, this fixes the gauge parameter exactly. Or another way of saying that, if you set GA equals to 0, then that's supposed to have a unique scope for a fixed value of A. And then you imagine varying that A with respect to theta. Setting GA equals to 0 has a unique solution on the space of gauge transformations. So just to make this a little bit more clear, let me give you an example, and this is the example we'll talk about for the rest of class today. Let's take G to be the divergence of A. Okay. And in particular, you could even take G to be the divergence of A plus some other function of X. So this is for any set of D functions, omega A of X. So that means that setting GA equals to 0 will uniquely fix the gauge parameter theta A up to some solution of the second order differential equation d mu times the covariant derivative of theta is equal to 0. And here I've written out, so here I'm just using the fact that under a gauge variation, A transforms by the covariant derivative of theta, and so G transforms by the divergence of that covariant derivative that I've written here. And so theta will then be fixed uniquely up to some solution of this differential equation here. And if we consider the case where A mu, the A mu's are very, very small, this is just Laplace's equation. d mu theta is equal to 0, which, at least in Euclidean signature, has a unique solution for specified boundary conditions. So if your gauge field is very small, so if you're working in perturbation theory, then this choice of the function GA is okay. So it will uniquely fix the theta A. I'll actually mention that there's a slight subtlety, which is that if you try and work beyond perturbation theory, so if you study the theory non-perturbatively, there's actually a slight ambiguity, which is associated with the fact that when A is not small, you actually have a correction term that's linear in A in this equation. So there could be more than one solution to this differential equation. And that actually leads to a slight ambiguity known as the Gribov ambiguity. And so if you're studying non-perturbative Yang-Mills theory, there is actually this slight subtlety because there's actually more than one theta that solves this equation. And so you need to be a little more careful when you're studying gauge fixing non-perturbatively. But at the level of perturbation theory and Feynman diagrams, this choice of functional G is perfectly fine. So we won't talk about this ambiguity anymore in this class. Although it does come up, for example, when people study non-perturbative approaches to QCD, for example, using lattice gauge theory or things like this. Okay. So now the idea is that we want to include only one gauge configuration per equivalence class under gauge transformation. So that means that what we'd like to do is insert a delta function into the path integral that sets GA equal to 0. To completely fix the gauge ambiguity. And now remember, we want to fix the value of theta, and there's one theta for each point in space-time. So when I write this delta function of GA, I'm not really talking about a delta function, I'm talking about a delta functional. Okay? So what I really mean, if you want to think about it a little more precisely, is a product of an infinite number of delta functions. where you take a product for each point in space-time, and you have to take the product over the value of that index A of the four-dimensional delta function GA at A mu evaluated at the point X. Or, to write this out a little bit more explicitly, it's the divergence of A mu minus omega A evaluated at the point X. So you're really thinking about a product of an infinite number of delta functions. It's a delta function. It's the analog of a delta function for a path integral rather than a normal integral. Question? Oh, yeah, I mean, the only point is that in arguing that the G's uniquely fix the gauge parameter, I use the fact that Laplace's equation has a unique solution if you specify boundary conditions. And in order to get this guy here to look like Laplace's equation, I had to neglect the term proportional to A in the gauge covariant derivative. Yes, okay, no, good. That's a great point. So remember, this gets back, actually this is an important point because there are two different conventions that we use. Remember, I've put the coupling constant out front here, okay? So I'm using this sort of geometric normalization where the coupling constant is the coefficient of the f squared term. I could rescale A by a factor of the coupling constant, and then I would just get I would move that coupling constant into the covariant derivative, right? So if you did that, you would move the coupling constant into the covariant derivative, and then, for example, you would have in the covariant derivative here, you know, where's a good formula? You would have, for example, a factor of G here, okay? You see what I'm saying? Okay. So, yeah, no, that's a great point. So what I really mean is that the coupling, so you could either say this is the coupling constant being small or A being small. And that's just because I'm working in this sort of normalization where I've rescaled A by a factor of G. That's an important point. I think different textbooks use different conventions. I don't actually remember what Schwartz uses. I know that Srednicki uses a different factor of G. He doesn't pull that factor of G out front, generally speaking. Good question. Good question. Other questions? Yeah, really, if I wanted to be super precise, I should probably say that G times the value of the gauge field in a particular momentum mode has to be small because I have a derivative here acting on that gauge field. Okay. So really what I mean by perturbative is some combination of G and an appropriate momentum, for an appropriate momentum scale. Good, good question. But we're not going to talk about this ambiguity anymore because we're only going to work in perturbation theory. Good question. Other questions? Good. Okay. Good. So the idea is that we want to insert this delta function into the path integral so that when we integrate over gauge fields, you use this delta function to do the theta integration. Okay? So that you're not integrating over the gauge parameter. However, there's one subtlety that happens when you do this, which is that we need to be careful that when we do this, we preserve gauge invariance. And what this means is that when we introduce this delta function of the path integral, we also need to introduce an appropriate Jacobian determinant to make sure that our path integral remains gauge invariant. So in order to understand this, let me just consider a very simple example. So let's imagine that we were doing a one-dimensional integral instead of an infinite-dimensional functional integral. So let's consider the following example. Okay. So let's imagine that we were doing the following integral. Okay. What we're really interested in doing is an integral that's like integral dx of e to the minus s of x. So here, x is supposed to represent the gauge field modulo the gauge parameter. But what we actually have is an integral dx dy, where here y is supposed to represent the gauge degree of freedom, and x is supposed to represent the gauge invariant part of the gauge field. And I've written s as s of x because the action is gauge invariant, so it's independent of y. Now, of course, this is a simple one-dimensional integral, so if you wanted to actually perform this lower integral where we have an integral dx dy, what would you do? You would just throw out the y part. You would throw out the integral dy. But we've seen that for gauge theory, it's a little bit more complicated because, well, the dependence of A on the gauge parameter theta is a bit more complicated. So how would you go about computing z a little bit more carefully? Well, what we could do is the following trick. What you could do is write z is the integral dx dy times the delta function of y times e to the minus s of x. So that would work. Okay, that just sets y is equal to 0. But more generally, I could set y to be equal to any function of x. And I would still get the correct answer for z. So this means that this path integral localizes on the solutions of y equals to f of x. So y is supposed to be the gauge parameter, and it's going to be some function of the gauge invariant part of the gauge field A. And so what we then do is then we can introduce a functional, or some function, g of xy, which has zeros, when y is equal to f of x. And what we want to do is insert not delta of y minus f of x, but delta of g into this integral. And so you can then just use the fact that delta of g of x and y is the same as the delta function that sets y is equal to f of x up to the derivative of g with respect to y. Okay. That's just the chain rule. So that means that z is the integral dx times the integral dy of the delta function of g of x and y times this Jacobian dg by dy, okay, times e to the minus s. That Jacobian is important because that Jacobian is there to make sure that the answer that you get at the end of the day doesn't actually depend on your choice of that function g. So previously, we introduced this functional g, whose, when we set it to 0, fixed fixed some gauge field in the equivalence class under gauge transformations. And we want to make sure that our answer doesn't actually depend on our choice of this arbitrary function g. Okay. So that's what this function, that's what this derivative does. And if we generalize this to n variables rather than just one variable, this would then be an n-dimensional delta function right here, and this would be a Jacobian determinant. So now, applying this to the case of gauge theory, we see that our path integral is now an integral dA of this delta function, where there's delta functional of our gauge fixing function g, times what's known as a functional determinant. So a determinant of the derivative of g with respect to theta. Okay. So here, now, if you want to think about it, this is a determinant not of an n by n matrix, but of an infinite by infinite matrix. It's known as a functional determinant. And what we need to do now is come up with a clever way of doing this functional determinant. Any questions before I continue? No questions? Is this more or less clear? No. I mean, okay, now is, so I told you it was going to get weird. Now is where it gets weird. So what is this quantity that I'm trying to compute? What I'm trying to compute here is the determinant of this operator. Okay. And what is the operator? The operator is the variational derivative of our gauge fixing functional g with respect to the gauge parameter theta. So what is that variational derivative? So under a gauge transformation, labeled by some parameters theta a, how does g transform? Well, g was the divergence of a plus some function that was independent of theta. So g goes to g plus d mu ab theta b. That's that just is the statement that A transforms by the covariant derivative in the adjoint representation. So that means that the derivative of g, the variational derivative of g with respect to theta, is an operator, and it's precisely this operator. So if we want to write it out a little bit more explicitly, remember our rules for taking functional derivatives. So the functional derivative of theta with respect to theta b means you just replace every theta b by a delta function. So the variation of GA at a point x with respect to theta b at a point y is this covariant derivative operator acting on this delta function. So delta g by delta theta is an operator, and it's this covariant derivative operator. And we need to take the determinant of this operator. Now, if this operator were an n by n matrix, we would just take its determinant. But here, the operator is a derivative operator. It's basically it's some sort of quadratic derivative operator that depends on the gauge field. So the question is, how can we take its determinant? So let me ask a question to see if you guys have been following along. So let's say that I had the following operator, the Laplacian operator, and I wanted to compute not its determinant, but 1 over the square root of its determinant. Can anyone tell me how I would compute that determinant? Well, you could use the trace identity. But let's say that we had an n by n matrix. Let's say you wanted to compute 1 over the square root of the determinant of an n by n matrix. Well, what would you do? You could introduce the Gaussian integral and just compute the Gaussian integral. So now let's say I had a Laplacian operator, not an n by n matrix. Well, what would you do? You would compute 1 over the square root of the determinant of the Laplacian operator is then the integral over, well, now this operator acts on functions, not on vectors. So an n by n matrix acts on vectors. This operator acts on functions. So you would perform that integral. But now it's not a regular integral, it's a path integral. And up to a total derivative. This, what is this? This is just the integral of the usual kinetic term for a scalar field. So what is so this is a free scalar field. And what is a free scalar field computes 1 over the square root of the determinant of the Laplacian operator for a living. That's what it does. That's what a free scalar field means. Okay, so if you wanted to compute the 1 over the square root of the determinant of Laplacian, you would introduce a scalar field. What if you wanted to compute a determinant, not 1 over the square root of a determinant? Anyone remember? We did it last semester. It was on the problem set, I think. Anyone know? If you want to compute the determinant of an operator, we can use the fact that the determinant of an operator can be written as the path integral, or in the case of an n by n matrix, a normal integral, over Grassmann variables. That is to say, non-commuting variables, rather than commuting variables. So in particular, let's say that we have some n by n matrix that I'll call M. Then up to some overall constant involving the normalization of the path integral. That determinant is given by a Gaussian integral over the Grassmann variables. Okay, so now we want to compute a functional determinant rather than the determinant of an n by n matrix. I mean, this is really what Grassmann variables do for a living. They compute determinants for you. And I believe that if we didn't prove this identity last class, but you had an exercise where you checked this identity, at least for a simple Gaussian integral, right? We did that. So now we just want to do this to compute a functional determinant rather than a determinant of an n by n matrix. So just as when we wanted to compute the determinant of the Laplace operator, you ended up introducing a new field here. In this case, it was a real scalar field that you added to your path integral to compute this determinant. Now we want to introduce a new Grassmann valued field. So let's introduce a field. I'll call it C, which is a complex Grassmann, that is to say, anti-commuting scalar field. Then the determinant of this operator is the integral over C and its complex conjugate, C bar, of the Gaussian integral where this Gaussian integral is the integral of so you have the integral of an action, so that's d for x, of c bar a. So what do you want? You want to compute the determinant of this operator here. So that's got to be the kinetic term. For your field C. Or if you want to write it out a little bit more explicitly, C is a new field that you add to your theory, whose kinetic term, which has the usual kinetic term, so integrating by parts, you get a d mu C bar A, d mu CA, and the covariant derivative leads to an additional term which describes an interaction between this field C and our gauge field A. So we conclude that in order to make sure that our theory is gauge invariant, in order to reproduce this Jacobian determinant that arises when we fix a gauge, we need to introduce a new field and add it into our action. And the sole purpose of this field is to compute this determinant for us. Yes?
Do we have 2 bars?
Oh, I'm sorry. Sorry, 1 bar. Sorry about that. Thank you. Oh, sorry. No. Good. Thank you. Sorry about that. The action should be Hermitian, of course. So this field C has a name. Okay. We call it a ghost field, also known as the Fadeev-Popov ghost. And its sole purpose in life is to make sure that we have an appropriate functional determinant in our path integral so that everything is nice and gauge invariant. An important point is that this ghost field should never appear in external states. You know, we're not interested in introducing a source for this ghost field and studying the scattering of this ghost field. But it does propagate in loops. So if we only are interested in tree-level physics, then we don't need to care about this ghost field. But if we want to study loops, then we need to introduce this ghost field. And because it's a Grassmann-valued field, an anti-commuting field, there'll be the usual -1 associated with every loop of the ghost field C. I mean, there's one thing that is somewhat disturbing about this ghost field, which is that it is a scalar, but it is anti-commuting. So if it were a real physical field, it would violate the spin statistics theorem. So if it were physical, that is to say, if there were actual states that you could create in the Hilbert space of your theory that you could study by quantizing this field and acting on it on the vacuum and studying the properties of those states, then it would violate spin statistics. So, for example, earlier last semester, we asked what would happen if you had tried to quantize a spin 1/2 field as a commuting scalar or a spin 0 field as an anti-commuting scalar, and you saw that there were deep problems that arose. There was problems with Lorentz invariance, problems with positive energy. There's something deeply wrong with anti-commuting scalars if they're real physical fields whose quantization gives you new states in Hilbert space. This ghost field is not a physical field. It's just some auxiliary quantity that we introduce in order to make sure that our theory is gauge invariant, and it never appears in external states. Sometimes there are cases where it can be formally useful to talk about states created by the ghost field C for sort of formal reasons, but you always need to keep in mind that the physical states of the theory only involve the physical fields, not the ghost fields. Okay. Are there any questions on this? Yes.
So the fact that we need to introduce anti-computing numbers comes from the fact that the determinant itself is anti-symmetric. Because it involves something purely from mathematics. Right?
Yeah. I guess you could say it that way. I mean, yeah, I guess you could say it that way.
Because the determinant is actually, you can write that as epsilon I j k times.
I guess you could say it that way. I guess you could say it. Good. Other questions? I mean, yeah. Go.
Why is this scalar?
It's a scalar. Really, why is it a scalar? It's a scalar because this differential operator that we're trying to take the derivative of acts on scalars, not on vectors. Because theta is a scalar. If you are considering, for example, the theory of gravity, where the analog of the gauge transformation is a diffeomorphic or a change of coordinates, the analog of the gauge transformation is a vector, right? It's the vector that generates a change of coordinates. And the ghost field that you would need to introduce is a vector of ghosts rather than a scalar of ghosts. For gravity, it gets even more complicated, actually, because you then have a ghost, you know, that vector itself has some gauge freedom, so you need to introduce a ghost for ghosts. Okay. It's ghosts all the way down. Similarly, if you study, for example, what's known as a theory, a gauge theory with a spin 3/2 field rather than a spin 1 field, that's known as the Rorita-Schwinger theory. In that case, you actually have a gauge parameter that's a spinner, and so you need to introduce a commuting spinner rather than an anti-commuting scalar. So, you know, the world is your oyster when it comes to ghosts. The nice thing is that ghosts only ever matter if you're computing loop effects. So if you're only interested in tree-level effects, which is largely but not entirely what we'll be studying, then you don't need to worry about the ghosts. Any other questions? I mean, yeah, it's really very clever. It's a very clever trick. Very clever trick. Good. Okay. There's one final, yes, question.
If we need to implement other symmetries, apart from gauge symmetry, maybe internal symmetries that involve fields, can we use it to consider in general?
Yeah, I mean, you know, if you have global symmetries, which are just n-by-n matrices that are not one matrix per point in space-time, but just an n-by-n matrix, for example, then there's no reason to introduce a field, because the reason why you have a field, that is to say 1c for each point in space-time, is that your gauge parameter was a field, right? It was a gauge parameter for each point in space-time. But if you don't have a gauge parameter for each point in space-time, but just an n-by-n matrix, then it's not really a field. Okay, you just have a determinant.
So if we have, let's say, a path integral over some three configurations, integral over d5, we need to restrict those phi to some particular class, the basic symmetry. So can we do that with...
Yeah, I mean, this is just a trick for computing determinants. So for example, there's this famous, I don't know, have you seen the Vandermonde determinant? Maybe that would be a good exercise, actually. There are certainly cases where you can use tricks like this to compute determinants. So this is not...
not saying about the term. I'm
Yeah.
saying in general about the purpose.
That's right. I mean, so for example, if you wanted to integrate not over a gauge field but over n by n matrices, and you wanted to require some symmetry under these n by n matrices, like say conjugation symmetry on the space of n by n matrices, there's a Jacobian determinant that arises. This is a sort of famous mathematics problem that arises all over the place, and you can treat that using ghosts just as we did here. I might try and come up with a clever problem on that. It's sort of a simple baby example of the Faddeev-Popov procedure. Okay. Maybe I'll make one comment, which is that if we were studying electromagnetism rather than Yang-Mills theory, I could say everything that I've said so far. And I could still introduce a ghost field C in order to implement my gauge fixing. But now, the structure constants would be 0. And so our ghost field wouldn't interact with anything. And so the effect of introducing this ghost in order to do the gauge fixing in electromagnetism would just be to multiply our path integral by an overall number. It wouldn't matter. The point is that in non-abelian gauge theory, there's a coupling term between the ghosts and our gauge field, which reflects the fact that this operator that we're taking the determinant of depends on our gauge field A. So that's why none of this arose in electromagnetism. It was sort of there, but it was just some overall number that multiplied the path integral. And when you actually compute correlation functions or observables, those numbers don't matter, of course. Okay. I have a, let's see. Good. Maybe I should just stop here. Okay. I did have one more comment that I wanted to make about gauge fixing, but we'll leave that for the beginning of next class, and then we'll start next class by writing down some final rules. So let me maybe just end and see if there are any questions. Okay, great. See you on Tuesday.